Hello everyone. We will continue the last class where we have left. We will continue from that. So, today's topic will be thermal processing and kinetics of microbial death. So, we have stopped in the last class in the calculation of the unsteady state conduction equation, which is the one dimensional Fourier's law of heat conduction. So, the solution was this, and using the boundary condition we have found that y is equal to 4 by pi exponential minus pi square alpha t by L square into sin pi x by L. So, let us see the terms here. We have seen that only first term of this equation can be taken for calculation of the temperature, where this parameter y equal to T minus T 1, which is the temperature of the sink, divided by T 0 minus T 1, and alpha is the thermal diffusivity of a material, L is the characteristic length of the body or the food that we are considering, and x is the dimension which is related to the distance from the center to the surface. So, we will see that this analytical solution that we have solved now has certain problem for using in actual case, because these analytical solution will depends on the different geometry, and often this is very tedious to solve. Okay. And also sometime it happens that we consider the parameter, the alpha thermal diffusivity, as constant parameter. So, also the thermal properties like alpha depends on k by rho Cp, these are also varies because of the composition, because of the composition of the material. Cp will also vary. So, there are different cases, okay, different conditions. For this, the lumped parameter approach that we have taken earlier has been changed to this, but again the difficulty of solving Fourier's law of heat conduction for the actual cases in actual geometries, we will further move on to a graphical solution. So, how we can solve in this graphical method is that graphical solution has been developed based on certain dimensionless parameter. So, first Garnier and Lurie developed this kind of a chart. So, based on the dimensionless temperature parameter y against the Fourier number f 0 as a function of two other variables, that is m and n. So, what is m and n? M is the reciprocal of the Biot number. Biot number, that is h into characteristic dimension L c by k. So, 1 by Biot number is represented as m. Okay. So, for a cylinder or sphere, the characteristic length will be the radius, and n is a dimensionless measure of the position within the object, defined by n equal to x by L. So, we have seen that x is the distance from the center. So, that distance divided by L, which is the thickness or characteristic length, characteristic dimension of the body. So, x by L signify the value of n. That means, if we say n equal to 0, that means it is at the center that we want to measure, and n equal to 1 means x is L. So, L by L is 1, that means at the surface we want to measure the temperature. Okay. So, graphical solution, if we see the Gardner-Lowry chart, so this chart is represented here. This is basically for the infinite slab. So, as we have seen that the geometry for different geometry, the characteristic dimension or characteristic length changes, because this is the volume, the surface area. Okay. So, this is characteristic dimension is the volume by surface area. So, therefore, it is changing for different geometry. So, this chart is specifically for the infinite slab. Okay. So, in the x direction, here x is represented by the Fourier's number, that is alpha t by characteristic dimension L c square. Okay. Y, that is in the ordinate. So, this is the dimensionless parameter relating the temperature. Okay. And this m is nothing but inverse of Biot number, and so m is varying here from 0 to 0.5, 1, 2 and up to m infinity. So, here so m is 0, then m is 0.5, then m is 1, 2, 6 and varies to infinity. However, the parameter in this is varying from 0. We have seen that n is equal to x by L. So, x is the distance from the center. So, n equal to 0 means this is at from the center, then gradually it is coming to the surface. So, 0.2, 0.4, 0.6 and 8, and n equal to 1 where m equal to 0, that is signified by this line, the ordinate. So, this is happening for all the different ratio of the 1 by Biot number. So, from this chart we can take the value of the parameter y. Let us say if we want to analyze that when a particular block, okay, having a known geometry or okay. So, this the temperature of this block, initial temperature T 0 is known to us, and then we are dipping it into a temperature T 1, and then we are calculating this y value, which is T minus T 1 by T 0 minus T 1. So, let us say we want to achieve a final temperature of T dash. So, when we reach the T dash, our process will be stopped. So, we put here T dash, calculate the parameter of this, the value of this y, okay, and we also check the value of Biot number. So, m, that is equal to 1 by Biot number, and also the distance from the center where we want to measure the temperature. So, let us take if we want to measure at the center. So, n will be 0, and based on this Biot number block, because this m is a set of equation, m is the set of equation set of lines here, set of lines, the whole line representing a particular m, that is 1 by Biot number. So, with the value required, we will see n equal to 0 and y value. So, let us say we are concerned for m equal to 0.5. So, this is the 0 value and here is the y value. So, we will connect them and then see what is the x value is coming. Okay. So, x is alpha t by L c square, the characteristic dimension. So, alpha is again k by rho c. So, K is the thermal conductivity. So, if the material is known to us, the thermal conductivity we can measure, density and specific heat is also known to us. So, then putting these value and characteristic dimension, we can measure the time required, so that the center of this food will attain the temperature T dash, which is required for the process. So, this is how we use the Garni-Lurie chart for getting the temperature profile at different time and different position. So, let us just once again think about the process we have considering now for the unsteady state process, and that will be eventually helpful in analyzing the heat treated preservation techniques. Okay. So, first we have seen the lumped parameter method. So, lumped parameter method we consider where the system geometry follows the restriction of the Biot number, that is B I less than 0.1, okay. And also it signifies that the internal conductive resistance is very low, conductivity is very high. Also in this case we assume that alpha is constant, where in actual case alpha varies, and also the measurement of the thermal property will also vary, and this use of lumped parameter can give us the temperature distribution with respect to time, but not with respect to position. So, then we have come to the analysis using the unsteady state one dimensional heat conduction equation, that is from the Fourier's law, and then we have derived the final form of the equation where the dimensionless parameter y can be related with the distance x from the center. So, in this pattern we can relate the temperature variation inside the food with respect to position and time, right. So, then from the same analysis we can perform by using this chart as well, just to simplify the tedious process of the analytical method. So, from this we can again move on to the next chart, which is the chart for infinite cylinder. So, this is the chart for infinite cylinder in the similar way as we have analyzed for the infinite plate. So, here is the value of x, which is Fourier's number, and here the y value, here the m value which is 1 by Biot number, and m value and n value which is x by L. So, the x is signifying the radial distance of the cylinder. Also for the sphere we can see this chart. So, this is for a sphere, and x is again represented in the towards x axis. In the y axis we are representing y, which is dimensionless temperature parameter. M and n are as representing the 1 by Biot number and characteristic or the reference position of the temperature measurement as it was for the earlier two cases. Now, the difference of this chart from the earlier two charts is that here we are measuring or we are getting data for a finite dimension for a sphere. However, in the previous two cases for infinite slab or infinite cylinder, we are getting one dimension is in a finite measurement, the others are infinite long. So, there is a problem for analyzing this chart, for using this chart for actual calculation, because what happened that in actual food process most of the cases the dimensions are finite, and in that if we use this kind of if you use this chart, so some error we may get, because if we are taking an cylinder if we can take a cylinder. So, what happened that we need to calculate the parameters in between the infinite cylinder and infinite slab. So, in that case the y, that is the parameter we actually need to take, we actually need to consider, will come as y plate into y cylinder, and then we relate this with other Fourier's number and the dimensions m and n. So, there is a problem, and most of the cases in the food sample when we go for preservation using the sterilization. So, we need to have the center point temperature because that is very important, because the assurance that no contamination will be there or no microbial growth will be there is very important for preservation of food, and to ascertain that we need to maintain the center temperature at a set level, or we can perform the process in such a manner so that the center temperature should attain the sterilizing temperature. So, for that the center temperature is very important. So, that is why further advancement in the chart has been done by Haeseler, and we will see now the other chart which is called the Haeseler chart, where again the Fourier's number is represented here in the x axis alpha t by r 0, or you can term it as again L c, which is your characteristic dimension square of that, and in the y axis we are having dimensionless parameter y or theta, like T temperature T 0 minus T infinity by T I minus T infinity. So, initial temperature is of the body is noted by T I here, T infinity is the temperature of the surrounding, and T O is the temperature it attained at any time. And what is being done here is the value of 1 by Biot number, that is very important. So, that has been varied from 0 to 100. So, this number has been varied from 0 to 100, because here we are considering the cases where the conductive resistance is very high, and also all these lines has been drawn considering n equal to 0. So, all such line has been drawn at n equal to 0, that means x is equal to 0 because n is equal to x by L. So, this is the center temperature. So, we can also get from this chart, if we plot Biot number, inverse of Biot number in the x direction, x axis, and theta by theta 0 in the y direction, and r by r 0 will be represented by this. So, we can calculate based on this what will be the temperature distribution inside the food. So, change in thermal energy storage. So, change in thermal energy storage can also be seen from this data, where the again Biot number is plotted, and q by q 0, that is the heat content change in the heat content over the initial heat content q 0, and this is Biot number square into Fourier number. Okay. So, from this chart we can get the thermal energy storage, the idea of the thermal energy storage. Now, this as I said that this kind of analysis will be varied for both if we consider the sterilization, or else if we consider the freezing. So, one problem of the similar kind has been taken here, where apple of whose the diameter is 120 mm, density is 990 kg per meter cube. specific heat 4170 joule per kg degree Celsius, thermal conductivity 0.58 watt per meter degree Celsius with temperature of 25 degree Celsius is placed in a refrigerator where temperature is 6 degree. So, that is our surrounding is at lower temperature. So, heat will come out of the material. Average convective heat transfer coefficient over the apple is 12.8 watt per meter square degree Celsius. Determine the temperature at the center of the apple after a period of 2 hours. So, let us see the solution. First, we will have to find out that if diameter is 120 mm, radius is 0.06 mm. So, characteristic dimension will be r by 3. Okay. So, this is volume of the sphere by surface area. So, r by 3. So, that is 0.02 meter. Again we will calculate the Biot number, that is h into characteristic dimension L c by k thermal conductivity. So, that is coming 0.44. So, this is greater than 0.1, that means we should not use the lumped parameter approach. So, we will move on to the graphical solution using the Hazelitt chart. So, 1 by B I is 2.267, Fourier's number f 0 that is equal to alpha t by L c square, that is equal to 0.281. Temperature at the center x by L or r by r 0, that is equal to 0. So, from the Hazelitt chart we will calculate the parameter T minus T 1 by T 0 minus T 1. Okay. So, we know all the parameter, that is 1 by B I and Fourier's number and also the n is equal to 0. So, using these 3 from the Hazelitt chart we can calculate the parameter of y. Okay. Now, once we calculate y, we need to know the temperature of the product, we know the. So, here we are getting all this for n 0, we can straight away take the value of B I Biot number that is coming, and then alpha t by r 0 square, that is Fourier number, and from this we can calculate straight away the value of the parameter theta. So, using that, here we are getting the temperature, dimensionless temperature parameter as 0.75. Okay. So, putting all the value we can find the T 0, that is 20.25 degree Celsius, right. So, this was our Fourier number 0.281 and 1 by Biot number, that was 2.267. So, we have taken here 2.267 somewhere here, this line for all n equal to 0 this is, and we have taken the Fourier's number data here and find the point where these two intersects and calculate the y value, which is the dimensionless parameter. So, this is how we can use the Hazelitt chart for calculation of temperature with respect to different center points for different time in case of the unsteady state. Okay. So, now another problem based on the Gourdini-Laurie chart, we will see where a meat slice 10 mm thick and initially at a temperature of 80 degree Celsius is to be cooled by blowing cold air at 2 degree Celsius. Estimate the time for the center of a slice to reach 20 degree Celsius, and the properties of the material is given here. K equal to 0.375 watt per meter Kelvin. Rho is the density of the meat, that is 1250 kg per meter cube, and C which is the specific heat, that is 2130 joule per kg Kelvin. Okay. So, okay. So, then we will see that solution, again we will find the characteristic length and the Biot number of this. So, m will be 1 by Biot number, that is 0.5. Here it is a slice. So, alpha equal to k by rho Cp, that we will calculate. Y the dimensionless parameter, that we will calculate, because we know here the final temperature and the initial temperature. And after getting this, F0 is obtained from this chart. So, this is for an infinite slab. So, here putting all the value, like putting the values of y at 0.231 and at the center where n equal to 0, and for the we can find the Fourier number. Okay. So, Fourier number is coming 1.4 using these value, and Fourier number is alpha t by L c square. So, it is 1.4. So, from here we can calculate the time, that is 248 second. So, this is how using the Heisler chart and Gurney-Lowry chart we can calculate the temperature profile in case of different food material when these foods are exposed to the higher or lower temperature surroundings. So, the principle we have discussed today, we will be using this one for the thermal preservation techniques that we will follow in our next class. So, till then, thank you.